Welcome. My name is Nick Vendegiesen and I'm Professor of Water Resources Management. To supply the world with sufficient water, we have some important tools. Last time we looked at reservoirs and now we will look at groundwater. When you run out of water, you may want to dig to see if you can find water underground. When you dig or drill deep enough, there's a very good chance you will find water. This water is groundwater. Groundwater flows through water-carrying geological layers or aquifers. The depth at which you find groundwater is called the water table depth.
So apparently the water is draining to a deeper level. Let's see if we can dig that deep. So there it is. We have reached the groundwater table.
People have known this for millennia and have dug wells accordingly. For example, in deserts from the Sahara to the Gobi, you can find Asian qanats, underground galleries that capture groundwater. Near the city of Gonabad in Iran, a 2,700 years old qanat still provides water to a population of 40,000. Groundwater is a bit mysterious. Why does it not simply run away? Why does it not flow deeper into the ground or to the sea? Actually, it does indeed flow down, but it does so very slowly. Water in a river typically flows at a speed of about 1 meter per second. An aquifer that conducts water at a speed of 1 millimeter per second, or 100 meters per day, is considered a fast aquifer. Often speeds of 1 meter per day or less can be found. The fact that groundwater flows at such low speeds means that it functions as an underground reservoir that we can tap. The water is there and does not flow away quickly. The low speed also implies that we can easily overexploit groundwater, as water will not quickly flow in from far away. Water moves from one point to another when there is a difference in groundwater table depth at these points. So if you would dig a well at point A and a well at point B, and the water table at B is higher than at A, water would flow from B to A. The water table depth is defined as the level at which the pressure in the groundwater is equal to the atmospheric pressure. When you would go deeper into the groundwater, the pressure increases just as it does in a swimming pool. At any point, you could insert a groundwater tube that is open at the bottom and closed at the sides. The water would rise into the tube until the pressure at the bottom of the tube is equal to the pressure of the surrounding groundwater. The water level in this tube is called the piezometric level. When the piezometric levels between 2 points differ, water will flow from the higher piezometric level to the lower piezometric level. We will now show how slow water moves through a sand column in a simple experiment which you can easily repeat at home. We have a column filled with sand which is saturated with water. When we open this tube, water starts to flow through the sand into this beaker. The amount of water flowing through such a column can be calculated using Darcy's law, named after Henri Darcy, who described this movement in 1856 in his design of the drinking water system of Dijon, France. Any given sand or other porous medium has a certain conductivity. Coarse sand typically has a higher conductivity than a very fine sand or a clay. When we increase the height gradient between the inflow and outflow points, flow also increases. Now that we know how water flows through the ground, the next question is, where does the groundwater come from? This is relatively simple. All the rainfall that does not evaporate back into the atmosphere, either directly or through plants, seeps eventually downward towards the groundwater table. This water is called groundwater recharge. A lot of the groundwater we find infiltrated locally, but it can also infiltrate upstream and move downward through the aquifers. Sometimes water infiltrated a long time ago under a different climate, and this water is still available to be pumped up. A famous example is the aquifer complex of the Nubian sandstones under the eastern part of the Sahara, where water is pumped up that infiltrated 100,000 to 1 million years ago. Clearly, if the recharge into an aquifer is less than the water pumped from an aquifer, the groundwater table will fall. At some point, it will then become economically unfeasible to pump more water up because the pumping costs become too high. Exploration of an aquifer is never sustainable when extraction is less than recharge. Groundwater is being used around the world for drinking water, industrial process water, and especially agriculture. A famous example of agricultural groundwater use concerns the Ogallala aquifer, one of the largest aquifers in the world. The Ogallala underlies much of the high plains of the United States and runs from South Dakota in the north to Texas in the south, covering about 450,000 square kilometers. Groundwater pumping for agriculture started in the 1940s. Today, about 26 cubic kilometers per year is pumped from the Ogallala aquifer, about 30% more than the natural flow of the Colorado River. This is the equivalent of 55 millimeters per year over the complete aquifer. The high plains are relatively dry, so in most places, recharge is much less than the amount of water extracted. This picture shows the resulting drop in the water table in feet from 1980 until 1995. Clearly, in many parts, the level is dropping at alarming rates. In the south, in Texas, there is a rise, but this is due to the fact that the water table there had declined so much by 1980 that pumping had become uneconomical. A similar fate awaits several counties in Kansas in the coming decade. Other parts of the world, and especially parts of Asia, suffer even more than the United States from groundwater overexploitation. This map from a famous article by Wada et al. From Utrecht University shows global groundwater depletion. The Arabian Peninsula, Iran, the North China Plains, and especially the Indo-Gangetic Plain stand out. The Indo-Gangetic Plains run through Pakistan, India, and Bangladesh and are home to 600 million people. Groundwater extraction due to irrigation here is so large that it changes the gravitational field of the Earth in such a way that it can be measured from space by the GRACE satellite. This image from an article by Tiwari et al. Show a decline of about 40 millimeters per year over this huge area. Building reservoirs slows down the hydrological cycle because the residence time of water in river systems increases, often dramatically so. Present storage capacity of all reservoirs exceeded the total annual runoff through rivers in the world. One way to think of this is the equivalent amount of sea level drop. Because water is stored in reservoir, it is not available in the oceans. Reservoirs have, therefore, had a lowering effect on global sea levels. In contrast, pumping of groundwater has an accelerating effect on the hydrological cycle because water flows through aquifers at a slow pace. Pumping the water to the surface from where it either flows into the river or evaporates into the atmosphere speeds things up. If aquifer depletion exceeds aquifer recharge, the amount of water stored in aquifer reduces. Mankind now pumps so much more water from aquifers than is recharged that this also has an effect on sea levels. As you can see in this graph, humanity's net effect through direct intervention in the hydrological cycle by building reservoirs and pumping groundwater is additional sea level rise. Of all fresh water on Earth, not captured in ice caps or glaciers, groundwater takes up about 98%, of which roughly 1/3 can be found in Antarctica. So with the continuously increasing demand for fresh water, exploitation and overexploitation of groundwater is likely to continue for decades to come.